Okay, good morning, everyone. It's a pleasure to give a keynote introduction to you all, and I hope you can also acoustically understand me in the back of the room. Thank you. So, as the title says, I will talk a little bit about the CO2 neutral energy supply systems and how we, from a viewpoint of power electronics, see the future and how this would impact the grid. And I understand that in reserve, as Professor Monti already introduced, you're looking how to dynamically keep this stable. I strongly believe that with power electronics, we have very fast response times that actually we can make the grid more stable. Another thing that I want to give as an introduction here today is that we see more and more the use of DC technology. 125 years ago, Edison did not have the DC transformer. Sometimes we call it solid state transformer or DC to DC converters. If we would have had that technology at that time, we would never have had an AC distribution or transmission system, because that was a compromise between the more efficient DC technology at that time and the AC technology. The invention of the transformer gave us the possibility of changing voltage and transmit power over long distances more efficiently at high voltage. So just a quick introduction. We also have here, together with the Ion Center and many industry partners, and you see their logos here at the bottom, about 21 companies, we are working on flexible electrical networks. And this spans several activities working here together on campus. This is a very large project supported by the federal government, Ministry of Education and Science here in Germany. These are the topics that we cover: DC grid systems. This is headed scientifically by my colleague, Professor Moser. DC grid components, I'm leading that group. Digitalization is led by Professor Monti. Then we also look into social, economical, environmental aspects. We look more and more into, for instance, the whole value chain and the ecological balancing of equivalent CO2 emissions, and there are quite some surprising elements coming out of that. And then together with the companies who work on standards, we are very active in the medium voltage DC standardization that is starting at SIGRE. It's a working group C631, which was created June last year. So some of the things that we realized so far, as you can see, this box here is actually a transformer of 2.3 MVA at 1 kilohertz, and about, you could say, 15 times more compact as compared to a 50 hertz transformer. And at the same time, together with the DC to DC converter, which actually is a 7 megawatt peak, but has its highest efficiency at 5 megawatts, we can transmit 7 megawatt of power at efficiencies at rated conditions of more than 99%. And so this is as good as a 50 hertz distribution transformer, but consumes far less material. And overall, it would be a technology that would allow us to save a lot of copper, silicon steel, and materials that require a lot of energy to be produced. And that is also important. It's not just about saving energy and electrical energy, but also the whole value chain. One thing that we also do in this project, and we just are about finishing that, between the lab that you will visit tomorrow, our 5 megawatt test facility, and the Center for Wind Drives, and coincidentally this afternoon they also start their annual conference, parallel to Reserve, we made this 5,000 volt DC link, which are 4 cables, so plus minus going back and forth, so we have a ring bus, and so we can test basically the multi-terminal DC grid structure. And those two buildings that you see here are being, the one in yellow and blue, are new centers that are being constructed, which will also be running on DC technology as a demonstration. So what I'd like to talk as an introduction is about the CO2 neutral electricity system, and then focus a little bit about what are the requirements that we see coming when e-mobility arises and all the vehicles would become electrified. I'm a strong believer that that would be a plus, because then we have a huge capacity of demand side management to take into account and take the volatile energy from wind and photovoltaic. So this is also again an opportunity and not really a problem. But I like to introduce that to you also a little bit to illustrate that we can really handle 100% all the vehicles in, for instance, in Germany as a case analysis here, being electrified. And the most important thing about e-mobility is to reduce the local emissions. That is the first thing. So ultimately, we can do it 100% CO2 neutral. So this is just for Germany, and you know that at this moment, most of the investments in wind turbines is done in the north, on the North Sea offshore, as well as photovoltaic more in the south because we have more sunny days as compared to Aachen, which is somewhere located here. And for that reason, we see that basically in the summertime, that we will have to transport, if we keep doing this, the way we are doing this in Germany as an example, more than 20 gigawatt of power from solar energy to the north of the country, and in the wintertime, 20 to 30 gigawatts of power from the north to the south, if we install all the wind in the north and all the solar in the south. And that is, of course, not an optimization for the overall system, because actually the grid is far more expensive than the wind and the photovoltaic systems, the power plants. And so we really have to look into distributing solar and wind. And this is also something that policymakers should pay attention to. Do we need dynamic tariffs, or do we need also for the feed-in tariffs more regional tariffs, so that the investors can balance wind and photovoltaic more evenly? The advantage of this is that we can basically have a balancing effect between wind and photovoltaic, so that we need less storage capacity or controllable power supplies. For instance, one possibility that we are looking into the future, and then it will be definitely a business case at one point, is to have electrolyzers produce hydrogen, maybe methanize it, and then use this stored energy whenever we have no wind and solar. And this happens over an entire continent in Europe every 4 or 5 years in the winter time, that we have 2 weeks of no wind with very little solar energy. So we need a high capacity storage device, which will not be batteries and not hydropower alone. It will be most likely chemical energy storage in the form of gas that has been produced when we have too much wind and sun, for instance, in the summertime or spring and fall. So the distribution grid could become then more cellular, as it is shown in this slide. And basically, this is something that DSO sees more and more as a business case. Because keep in mind, the distribution grid is radial. And so if you have a distribution grid, and let's say, for instance, here in Aachen, on the one side, we have a lot of wind, while the city has a lot of photovoltaic installed, the only way they can exchange the energy is going through the high voltage substations. They have to bring the energy back to the top and then redistribute it. So if you have horizontal connections at the medium voltage level, and that technology can be best realized with DC interties, then you can exchange within your own grid the energy without having to sell it to a transmission system operator. And actually the TSOs also tend to like that, because if we feed in a lot of energy locally and take it out on the other side of a large city, we may locally overload the transmission grid with a lot of peak powers. So there's a lot to be said for what is shown here in this slide, that you have DSO regions which are cellular, interconnected, and then they interconnect with HVDC lines that can bring maybe not to 20, 30 gigawatts, because we have never built transmission lines that can transmit 20, 30 gigawatts. Typically, high voltage transmission lines can transmit 2 to 3 gigawatts, and that's about it. So this would allow us to exchange the energy locally, and this is why we work on flexible grids. Another interesting aspect to that is what you see here. This is a slide by now Professor Hoffmann in 2008, and he did for a case for Germany an analysis where you see from 100 to 180% on the horizontal axis of renewable energy sources. And on the vertical axis, you see the share of photovoltaic. And let's say we have 40% of photovoltaic, and in total we have, let's say, 160% of renewable energy, wind and photovoltaic. Then you can see that you need only about 2% of energy storage on average over a year. And that corresponds to about 2 weeks where you need, which is now the German word Dunkelflaute. That means in the winter time, no wind, a lull of wind. That's Dunkelflaute, when there is no sun, when it's dark. And this is the energy that you need to store in those cases. Like the El Nino in the Americas, we have every 4 or 5 years this situation in the winter time where we have no wind at all over the entire continent. So very bad air quality, and some of you may have experienced that already. So then we need this huge amount of storage, and I think that can only be happening with chemical energy storage. Maybe we still buy some gas from other countries to overcome that, but ultimately, and some detailed studies like the study ESIS, you can download that from the internet, from the Academy of Technology and Science, Acatech, as well as other academies, Academy of Science and Leopoldina. 500 scientists worked on those studies and showed that when we have more than 80% of renewables installed from the total capacity that we need of peak power, then electrolyzers becomes a business case, because then we will have moments, enough time, where the electricity will be otherwise at zero or negative prices. And that would basically allow us to create a business case, a business model for producing hydrogen and maybe also oxygen, because if you use both, the fuel cells become much more efficient than pushing air through fuel cells. So this is just a number to basically have this 2%. But what's very important, it assumes that you can flexibly redistribute the energy locally, because if you have to push all that energy to the top, as I already mentioned, the transmission system will not be able to handle that. So now we talk also a little bit more about the mobility, because it is really now taking off, I would not say exponentially, but at least it's accelerating. People buying electric cars and also gaining experience with that. And here are some numbers to have a feeling how much energy do we need to produce more if all the passenger and trucks in Germany, which is about 44 million vehicles, would be electrified. And this is based on the numbers that we have. For instance, you can see here that in 2016, Germany consumed about 525 terawatt hours of electrical energy. The grid peak load is about almost 84 gigawatts. Keep in mind that all in Europe we have over-installed capacity of big power plants. And these are all stranded investments because of the wind and the photovoltaic. Those big power plants are only working 3,000, 4,000 hours per year. So that's why there are stranded investments at that moment. So we have 44 million cars, and you can see about 626 billion kilometers per year. That means about 38 kilometers per day per car is being driven. And that is quite typical. If you check your average driving distance, you will end up more or less around these numbers. Very few people drive more than in a particular day than, let's say, 400 kilometers. I heard some statistics that is only 0.04% of all the drivers do more than 400 kilometers on one particular day. So if we look at the energy storage that we need and the energy consumption, then you can have two extreme conditions. If everyone wants to charge very fast, well, then you need 1,800 gigawatts, which is, of course, 21 times the installed capacities, and that is, of course, absurd. On the other hand, if we can manage this whole fleet and you charge during the daytime 24 hours distributed like we normally calculate also in grid distribution, then we need about 11 gigawatts of installed extra capacity, you could say, and that is only 13% of the grid peak load. And that installed overcapacity is already there. So there is no problem to electrify all the electric vehicles in Germany. So this is a picture that shows a little bit how we see the grid of the future, including distribution grids. Transmission is already, of course, interconnected, as we all know. This was for safety reasons of nuclear power plants. When I was studying, I was going for nuclear engineering. And that was one of the reasons why we interconnected the transmission grids at the central power systems. The reason being is that the nuclear power plant, the cool water pumps always have to keep on running. And they take about 5 to 8% of the electrical energy that comes out of a power plant. So these are big units. And that is why if one nuclear power plant would drop out, energy has to be fed to that power plant, and other power stations can take over the energy so that the transmission grid never goes out. So that was one of the main reasons why we have interconnected that. The distribution grid is radial. In this picture, we see our future also interconnected all the way to the low voltage. And what is interesting to see is that in Germany, the installed capacities are already in peak powers, one third, in medium, high voltage, and low voltage. And this is what something that we predicted many years ago. If we have decentralized power generation and a lot of electrical loads, including heat pumps in homes and buildings, the energy production will move to one third. Because when you do that, you save a lot of transmission cost, not pushing the energy always to the top and then back to the bottom. So this is what is happening is also that we will see that the terawatt hours produced will move to one third. That is still not the case. This is the peak installed capacities. So let's take a look then at the e-mobility, because today there is a lot of discussion that the electrical grid simply cannot take that. And I already showed you that if we manage it well, it shouldn't be a problem, provided that the distribution grid is also, let's say, more interconnected and not radial as it is today. So I like to show this slide here, which is a simple calculation, and this is maybe to give a feel. The average speed on the German highways, even when in some cases you can drive 400 kilometers an hour, if of course then you don't have insurance, then basically the average speed is about 100 kilometers an hour. So if you drive 6 hours non-stop, with a diesel car, for instance, you can do 600 kilometers. So this is what does on the horizontal axis. You can see 600, and you would do that in 6 hours. So if you have a fast charging system, let's say a car that can take a range of 500 kilometers, maybe 100 kilowatt hour battery, and let's say you can charge with 2C, so with 200 kilowatts, then you can see here, that is basically the red curve. You would, in 6 hours, only need 25 minutes more time to do the same distance. So to do the same distance, or you could say, yes, this is how this has been expressed, 25 minutes. Now, keep in mind, for your insurance, you're not supposed to drive 6 hours non-stop with your diesel car. You have every 2 hours to make a short stop. My car gives that alarm automatically. Most of us ignore it, maybe, but that means that even a diesel car would also need a little bit more time to drive the 600 kilometers. What is also interesting is that if you leave a city, you're on the highway driving non-stop 100 kilometers an hour on average, you come back into the city, that is where you lose your time. And this is where basically the difference between an electric car and a diesel is no difference whatsoever. So we can also do battery swapping, and then you only gain 15 minutes. So this is why battery swapping has not been considered a real business case, because the end user also doesn't see the advantage of it. Also, when we all drive on vacation, that's the moment where we need a lot of batteries to be swapped, and the rest of the year no one needs it because we only drive on average 38 kilometers per day. So that is the reason why this is a very difficult proposition. But you can see there is indeed at least along highways. And the interest is there to charge with at least 150 to 200 kilowatt. If we ever achieve 350 kilowatt, which is what Daimler and Porsche are aiming at, that is quite debatable if we are willing to pay the price for that. Keep in mind, the higher the peak powers, the higher the temperature of the batteries get, and the more cooling systems you have to install, including also taking into account the efficiency of the charging stations, which goes down too. So that is quite an issue at this moment still. So here's some numbers. Again, these are the number of kilometers per annum, and this is calculated of so many million kilometers per day. And then we can basically calculate along the highways if we charge with 28 kilowatt hours, which is the average refuel capacity that would be needed, which is equivalent to 175 kilometer extra range. Then basically think about it. If you buy a Tesla, you have 500 kilometer range and you want to drive 600 kilometers, you only have to tank on the highway in between 28 kilowatt hours. So this is the average that corresponds to that. And that basically means that the peak power along the highways would be 2.4 gigawatt on average that needs to be installed. So this is another number. Along the highways, we need about 1,040 charging points. You can see in Germany today there are about 358, but they're only 50 kilowatts. So this is going to higher peak powers. And again, this shows the 2.4 gigawatts along the highway as a point of service where fast charging would be needed, which is effectively not really a problem to provide that capacity. Of course, we have to find business cases so that the people who invest in these fast chargers can basically have a business case in that. Along supermarkets, and this is opportunity charging where we have more time. Usually you're half an hour to an hour in the supermarket. There the peak powers can be less, but there would be maybe much more cars on the parking lot, so that again you also end up with peak powers that could reach several tens of megawatts. This is another calculation that looks into the charging at work. The downside of that is that most of the photovoltaic systems may be in the city and homes, and so how do you bring the electricity from the cities to the factories where people are working during daytime? And this is also, there's a lot of blockchain going on, that people bring the charge from home to the company and then get it back in the evening, and that there is some kind of balancing that is being calculated over a year time. But the interesting thing at charging at home between 8 p.m. and 6 a.m. in the morning, that would be, in order to install and charge the cars that we all have, entire Germany, that would mean 24 gigawatt of peak power at night. But that is very good, because at night, the peak powers that we ever had in Germany is 50% of the 80 gigawatts. So we have about 40 gigawatt capacity left. So that is not a problem whatsoever. During the daytime, where we have the peaks, when we have solar feed in, that would also be compensated fully by the 17 gigawatt that is needed if we all charge during the work from 6 a.m. till 8 p.m. So this is to see how would be the charging done. And of course, we will have a mixture of both. So this could be the future. You have a home which has an internal DC system, distribution system for all the hardwire equipment, like a heating pump system, a photovoltaic. You could have maybe a 50 kilowatt DC bus peak power for fast charging of a vehicle, connected to here a low voltage AC 400 volt 4-wire system, and that would be a possibility to take a look at. But we see a problem coming with a low voltage AC distribution. If you basically look here, this is a typical street in Aachen, with about a total of, as you can see, 60 households. And the way they calculate a transformer is that on average, every household takes a peak power of 3.6 kilowatt on average. you have basically a connection here in Aachen typically that can be 43 kilowatt peak power. So you can charge your car with 20 kilowatt. Now, if everyone would have a car with 20 kilowatt charging and plug it in at the same time, then we of course have a big problem, because then we need 630 kVA of power. Even when you have only a few cars, as it is shown here, with 40 kilowatt peak chargers, at the same time, it would be a problem also. So we have to manage this in a careful way. So the way we think about how we can solve these problems, keep in mind the capacity of generation is not a problem. It's how we distribute the energy there where it is needed at a particular moment in time. And here you can see the distribution grid from high voltage down to low voltage. The installed capacities of our transformers is actually at least a factor of 2 overrated compared to the installed capacity of the end consumers. The reason for that is these transfer switches. We talk here in Europe, in most countries, of an open ring bus structure. That means if you have a failure, as you can see in this slide, on the left-hand side, one of the feeders is interrupted. We close the medium voltage breakers. So first we open the circuit and then we close it. And now the other substation is delivering 100%. That means in that situation, I have to make sure that this transformer on the right-hand side top can deliver 100% of the power. This is why in normal operations, they are never overloaded more than 50%. Actually, I hear numbers from most utilities that their transformers are on average never used more than 30% of their installed capacity. This is why they eliminated all the blowers and the cooling systems over the years. So there's a lot of installed capacity, and if we interconnect the medium voltage substations with the medium voltage DC, and you can of course do that also on the low voltage, and there's still a debate where this is the best thing to do, then I can always draw the 50% overcapacity through the DC bus from one substation to the other and create basically this interconnection. And whatever installed capacity that is not used, I can provide for fast charging. And of course, people that do fast charging will have to pay a little bit higher fee than those who do slow charging and are willing to charge the car maybe based on a load management system. So this is the vision that we have, and this is how hybrid grids come about with DC interconnects. And of course, the more substations you can interconnect, the more of that peak capacity you can move in the cellular structure that you create with DC technology. So the key enabling technology for that is, as already mentioned, we call it a dual active bridge. It's a bidirectional DC to DC converter. Actually, it consists of a standard three-phase inverter. This is actually stacks from ABB large drive systems, medium voltage. So we have DC 5000 volt. We have the three-phase transformers. In this case, we built in the first years 3 times single phase, and then we have a three-phase inverter. The inverter is never switching in PWM. It is basically controlled by phase shifting the input inverter versus the output, and this is why we get these very high efficiencies. So what we could think of in the future in order to realize this concept of controlling flexibly the power and redistribute it is, instead of an AC low voltage distribution, we have a 5 kilovolt or plus minus 5000 volt. We still don't know what the standard will be. 5000 volt as an example here. Each house has a box, maybe a peak power installed of 5 kilowatts. And for 5 kilowatt, you pay a monthly fee of 50 euros. I would take it immediately. Because it is independent of how much power you take over the daytime. So if you take 5 kilowatt over 24 hours, if you can redistribute the load in your house, you basically have 120 kilowatt hours of energy every day available. And of course, you would have PV, maybe you have some storage, you have a heat pump system, and you have your electric car as a load. And most families have 2 cars. So at least one can be electrified to basically exchange also the energy between the neighbors. And this is something that we like to basically also demonstrate in some of those new large projects. Are we allowed to exchange energy between our neighbors? How do we handle that? Maybe with some kind of blockchain mechanism. One thing that is for sure is that DC was never regulated. So the regulator will have to act soon, because otherwise we will do it anyway. At the same time, cold and hot water systems may be also locally distributed in some kind of localized heating grid. And also that has to be checked, how we deal with that. So these are the things that the new technologies offer us. We can interconnect at a low voltage, at a medium voltage, multiple end users, and also prosumers, people and companies that produce electricity. And by this interconnection, we have a totally new way of handling this. At the same time, of course, there are also still technical questions of stability. Also, how much energy storage do we need? But the more flexibility we have in the grid, the more we have interconnections, the less energy storage we need. Except for those 2 weeks every 4 years where the whole continent won't have enough solar and wind energy, there is nothing to redistribute. Then we rely on storage capacity systems. So this is basically what my message is. Power electronics allows us to go very efficiently and transform very efficiently with very high efficiencies, above 99%. We are aiming that in substations, and maybe 98.5% in the low power, the low voltage systems, to transform high voltage or medium voltage to low voltage and vice versa. The trend that you see in your computer power supply, when I had my first desktop computer, which was actually supposed to be, it was an Olivetti transportable. It had a 50 hertz transformer. The thing weighed about 5 kilograms, the transformer alone. Now your power supply is switching at 140 kilohertz, typically, or just below that. And you have 120 watts for less than 100 grams. And this is the same thing that we should be doing with distribution transformers. Keep in mind the picture that Professor Monte showed in the introduction in Niagara Falls. Those generators were working at 133 hertz. 60 and 50 hertz came later because of the impedance of the wires, of the lines. There was too much voltage drop at higher frequency. With DC, there is no reactive voltage drop. There's only resistive voltage drop, which is about 8 times less than the impedance, the ohmic impedance of the reactance in transmission systems.